Welcome to This Explainer. Today we're jumping right into a fascinating mathematical mystery that dates all the way back to 800 BC in India. We're going to unlock the secrets of Baudhayana's Shulba Sutra, an ancient text that honestly will completely change how you look at geometry. Forget about memorizing those dry formulas from an old textbook. It is absolutely amazing to realize how these early mathematicians used highly visual, tactile methods to solve some seriously complex spatial problems. So let's just dive right into it. We're starting with a deceptively simple puzzle originally posed by Baudhayana himself. How do you precisely double the area of a given square? Now, it sounds like it should be an easy task, right? Just, make it bigger. But the real constraint here is precision. You need a brand new square that contains exactly twice the area of the original one. No more, no less. I mean, your first instinct might be the most common one. Why not just double the lengths of the sides? Say your square is 1 inch by 1 inch, so you just draw a 2 by 2 inch square. But actually, scratch that. If you really think about that for a second, you end up with a square that can fit 4 of those original squares inside it. Doubling the sides makes the resulting area 4 times larger, not 2. So yeah, that approach doesn't work at all. Instead of just endless trial and error, Baudhayana drops an incredibly elegant solution in verse 1.9 of his Shulba Sutra. He literally says, the diagonal of a square produces a square of double the area of the original square. Instead of messing around with the outside edges, he realized the secret actually lies inside the shape itself, right across the middle. By taking that diagonal line and using it as the base side for a brand new square, boom, you perfectly solve the puzzle. To really picture why this works, imagine a physical piece of paper. If you have an identical paper square, cut it into 4 triangles along both of its diagonals. Okay, got it? Now, take those perfectly cut triangles and arrange them right around the straight outside borders of your first square. You instantly create this new, larger square, kind of rotated on its side, made entirely of the original square, plus the exact area of that second square. You have tangibly, undeniably doubled the area. And here is where it gets really profound. This simple tactile geometry trick of building squares on diagonals naturally leads us to formalize one of the absolute most fundamental rules of mathematics. We know it today as the Baudhayana-Pythagoras theorem. It states that if A, B, and C are the side lengths of a right-angled triangle, where C is the long diagonal hypotenuse, well then A squared plus B squared perfectly equals C squared. We can actually take this a step further and explore a brilliant visual proof straight from the text. Instead of relying entirely on abstract algebra, just imagine arranging 4 identical right triangles. If you place them so their hypotenuses form a new 4-sided figure right in the center, the angles naturally align to make that inner shape a perfect square. And structurally, the area of this new square exactly equals the combined areas of the squares you could draw on the 2 smaller sides of the triangle. It's literally geometry you can see and touch. But this brings up a really interesting geometric reality. Think about what happens if we look at an isosceles right triangle. That's a triangle where the 2 shorter sides, A, are exactly the same length. Well, A squared plus A squared gives us 2A squared, which equals our hypotenuse C squared. That means C has to equal A times the square root of 2. And suddenly, ancient mathematicians hit a frustrating snag. The square root of 2 is a decimal that never ever terminates. There's literally no way to write it as a simple fraction of whole numbers. But let's face it, we humans love order and neatness. So what if we want to avoid those messy, never-ending decimals? Well, it turns out when the sides of these right-angled triangles miraculously work out to be perfect, clean, whole numbers, like 3, 4, and 5, or 5, 12, and 13, we call them Baudhayana-Pythagoras triples. These integer combinations perfectly satisfy that A squared plus B squared equals C squared rule without a single leftover fraction. Now, knowing that these perfect whole number triples exist is great, but it naturally leads us to another question. Since mathematicians have proven there are infinitely many of these triples out there in the universe, how do we actually find them? Are we just supposed to guess and check numbers forever? Ancient thinkers asked the exact same thing. Is there a systematic, secret pattern to easily generate completely new, primitive triples from scratch without all the guesswork? The answer lies in a beautiful, almost magical numerical pattern. Get this, if you stack consecutive odd numbers row by row and add them up, their sum always perfectly aligns with a square number. Think about it. 1 is 1 squared. 1 plus 3 is 4, which is 2 squared. 1 plus 3 plus 5 is 9, which is 3 squared. This pattern just keeps going, holding up infinitely. By expressing this logical pattern algebraically, we uncover a massive shortcut. We can officially declare that the sum of the first n odd numbers will always, without fail, give you n squared. Since any given odd number can be written as 2n minus 1, we've just linked the simple addition of odd numbers directly to the geometry of squares. We've unlocked an incredibly powerful mathematical tool here. Let's actually see this tool in action to generate the classic 3, 4, 5 right triangle. Watch this odd number magic trick. Take the number 9, which we know is 3 squared, right? And it happens to be the 5th odd number in our sequence. Well, what is the sum of the first 4 odd numbers right before it? It's 16, which is 4 squared. So 16 plus 9 equals 25, which is exactly 5 squared. 4 squared plus 3 squared equals 5 squared. We just generated a Baudhayana triple purely by understanding how odd numbers stack. How cool is that? So, armed with this incredible method of using consecutive odd numbers, the text throws down a challenge. It is puzzle time. You now have the exact conceptual tools that these ancient mathematical masters used. Take a second to think. Using that exact same logic of finding an odd square and adding it to the sum of the previous odds, can you logically deduce 5 more of these triples on your own? But as you play around with these numbers, a deeper mystery starts to emerge for you to ponder. This odd number method is undeniably neat, but is it exhaustive? Does this specific method sometimes accidentally spit out non-primitive triples, meaning just scaled-up multiples of smaller, simpler triangles? Or, even more intriguingly, does it skip over certain primitive triples entirely, leaving some beautiful whole number triangles undiscovered by this specific formula? And here is the kicker. This is not just some isolated piece of ancient trivia. This practice of finding patterns in squares and exploring these exact questions is so profound that thousands of years later, it directly inspired Pierre de Fermat. This 17th century French mathematician looked at these very principles and was driven to formulate legendary, incredibly complex theorems about the sums of powers of positive integers, ideas that literally shaped modern mathematics. Talk about a legacy, right? To leave you with a final puzzle from our source material to really test your new geometric mastery, imagine a completely infinite grid of dots stretching out forever in every single direction. If you use those dots as the corners, what are the possible whole number areas of the squares you can draw? Can you draw a square with an exact area of 2? What about 3 or 5? Think about those diagonals. Think about the theorem we just explored. It's an amazing mental playground, and I highly encourage you to grab some paper, draw out a grid, and keep exploring.